Okay, so we are recording, and let's just review. Last time at the end of class, we talked about the curl. So section 13.5 deals with the concepts of curl and divergence. And these concepts are helpful in terms of fluid flow, electricity, and magnetism. They play a basic role in regards to vector fields. So an electric field, you could model the vectors using it's a vector field, right? How many have seen like electric fields in one of their courses? You've seen gravitational field. How many have seen like electric fields in maybe one of their courses? Okay, Charles has, and Juliana, yes, in physics. So, you know, this is very applicable. So we learned that the curl of a vector field is given by these components. And these components are difficult to remember. Okay, so your vector field has components P, Q, and R, and the curl of the vector field is defined as this vector field. The curl of a vector field is itself a vector field. But this is difficult to remember, that definition. And so we defined what's called a del operator. And if we were to take that, the del operator here, if we were to take that, and if we were to essentially take the cross product of the del operator with the vector field, it would produce the curl of the vector field. And so now we have a definition, we have a way to easily find the curl of a vector field without remembering the complicated definition. And so they do an example here where, in example 1, where you have a vector field, and this is, we talked about this, they have a vector field, and they want you to find the curl of the vector field. And so they set it up, and they get the curl of the vector field. So are there any questions on that? They use the cross product of the del operator with the vector field itself. All right, well, let's continue then. So the curl is very nice because, well, for one thing, the curl of a gradient field is equal to the zero vector. The curl of a gradient field is equal to a zero vector. This means then, if you have a potential function f, if you have a vector field f that has a potential function, okay, and remember, what's that mean? Well, if you have a conservative vector field, okay, and if you have a conservative vector field, and that means that the gradient of some potential function f equals the vector field, then the vector field f is conservative, and so the curl of that vector field f is equal to the zero vector, because the curl, I mean, what I'm trying to say, let me say it the way I want to say it here. Sometimes it's easier just to show it on the whiteboard here. But if your vector field f is the gradient of some potential function, then the curl of the vector field would be equal to the curl of the gradient of your function. And that is equal to the zero vector. Okay, the curl of the gradient field, that's what this is, the gradient field. How many remember the gradient field from MATLAB assignment number 5? How many remember drawing gradient fields to help you determine whether critical points were maxima or minima? How many remember that from MATLAB assignment number 5? Sure, Ellie remembers doing that. And so, well, all right, so the curl, if if your vector field F is a conservative vector field, then that means that the vector field F is the gradient of some potential function. But the gradient of the function, of any function, that field, that gradient field, the curl of that equals the zero vector. So this establishes that if you just were to take the gradient of your vector field and does that equal zero? If so, then automatically you know that you have a conservative vector field, because the curl of the gradient field is equal to the zero vector. And so that means your vector field can be written as the gradient of some function. In other words, a potential function exists. Okay, so that's one reason why the gradient, or why this curl is very helpful. Because again, in section 13.3, you had criteria there to determine if a two-dimensional vector field was conservative, but you didn't have criteria to determine if a three-dimensional vector field is conservative. And now you do. Now you do. And so that being said, you could look at a vector field and just compute its curl and determine if the vector field is conservative or not. And if the curl of the vector field is non-zero, equal to the non-zero, it's not a zero vector, then you have a non-conservative vector field. And therefore you can't apply the fundamental theorem of line integrals to compute the work that vector field would do in moving a particle from an initial point to a terminal point in the field. So there's the theorem. There's the theorem that we just were talking about. What is, like, physically, how do we interpret the curl? Well, let me show you there now. So now we're continuing on. This is like review what we just did here. But there's a comment here. So the reason for the name curl is that the curl vector is associated with rotations. Okay, one connection is explained in exercise 37. You can look at that in the textbook, but another occurs when the vector field represents velocity field and fluid flow. Okay, see example 3 in section 13.1. Let me just look at that real quick. One moment. Right, so in example 3, section 13.1, they talk about velocity fields. So what they're saying is that particles near a point in a fluid tend to rotate about the axis that points in the direction of the curl. Okay, absolutely amazing. And the length of this curl vector is a measure of how quickly the particles move around the axis. So if the curl of a vector field F is equal to zero vector at a point, then the fluid is free from rotations at that point, and the vector field F is called irrotational. Okay, so an example, for instance, of can anybody name me an irrotational vector field that you're living in? That's correct, Juliana. That's right, the gravitational field. The gravitational field, if you were given the gravitational vector field, and you were to compute the curl of that vector field, you would get the zero vector. Okay? Gravity is not causing you to spin around, right? That's not what's causing you to, what I'm trying to say is, if you just look at the effect of gravity on your body, it doesn't cause you to spin around, right? That's something else that causes you to do that, right? Like wind or something, right? So the gravitational field is an irrotational irrotational. There's no whirlpool or eddy at any point in the gravitational field. Okay, and so I always like to think of nice examples. Here's though, if you here's an example of where at a point X, Y, Z, there's a little whirlpool or eddy around that. How many have seen that maybe like with like leaves? Like how many have seen like like leaves swirling around in a circle, like when the wind, like in the wind? How many have seen kind of that? Or a tornado? Hopefully you haven't seen a tornado, but it's okay. Charles knows what I'm talking about. And a tornado is another example, right? How many have seen the movie Twister? The movie Twister? That's an older one, um, but that's a movie involving tornadoes. And but the curl vector points, uh, uh, like you see there in figure 1, you have a whirlpool around the point X, Y, Z. The curl vector points out there, okay, along that axis. And particles of the fluid rotate about that curl vector, that vector, okay. So, okay, that's the idea of the curl. Now, are there any questions before we move on? Okay. Well, there's something else then important too in section 13.5, and that is called divergence. Okay, so not the movie Divergence. Okay, how many have heard of the movie Divergence? That's a newer one. Some of you, I'm sure, have heard of that. But divergence, how's that defined? Well, divergence on a vector field says, suppose your vector field has components P, Q, and R, and suppose the partial derivatives exist. So the partial derivative of P with respect to X. So that's rate of flow in the X direction. Partial derivative of Q with respect to Y, that's rate of flow in the Y direction. And partial derivative of R with respect to Z, that's a rate essentially of flow in the Z direction. The divergence is the sum of those rates. It's the sum of those rates. And it is a scalar. Okay. Well, I want to be careful here. The divergence of a vector field is not a vector. It's not a vector. Okay. It's what's called a scalar. It's what's called a scalar field. Okay. So there's the definition. The sum of the rates is a scalar. You notice there's no I, J, or K there for the divergence. And you can, again, if we use that del operator, okay, we could use a little thing to help us remember the definition of divergence. Just take the del operator and dot it with the vector field, and that will get you the divergence above. Okay, so it's the very beautiful little definitions here. And so if we want to compute divergence, here's an example, example 4. Here you have a vector field given by xci plus xyzj minus y squared k, and they want you to find the divergence of that vector field. So very easy to do. Take a look there. So what they're doing is they are computing those rates with respect to x, y, and z. Okay, and again, the rate of the p component with respect to x plus the rate of the q component with respect to y plus the rate of the r component with respect to z. Add that up and you'll get z plus x times z. That's your divergence. Okay. Are there any questions? Are there any questions on what you're seeing here? Okay. Okay. Well, so they make a comment that here that if you have a vector field on R cubed okay, then the curl of the vector field is also a vector field on R cubed. We know that. But the divergence of the curl is equal to 0. Okay, so the divergence of the vector field defined by the curl is equal to 0. Okay, so let's show why that's true. Let's look at this, let's see why this theorem is true. All right, so here is the proof. So the divergence of the curl would be, okay, so the divergence of the curl would just be the del operator dotted with the curl. Well, the curl is equal to the cross product of the del operator and the vector field. So, okay, the dot product means, all right, well, you have the partial operators with respect to x, y, and z, and each of those operators are being multiplied, I want to be careful, it looks like they're being multiplied by the components of the curl, right? But, if you were to multiply the operator by each of those components, it would look like you had the second partial derivative of R, the second mixed partial derivative of R with respect to y and nx, minus the second partial derivative of Q, the mixed partial with respect to z and nx. And then, you have the other 4 parts there. And because by Clairaut's theorem, the mixed partials, the mixed partial, I want to say this the right way. This is Clairaut's theorem. Clairaut's theorem. So, hold on, one moment. Okay, good. Just hung up there. Another useless, worthless call. I swear, I get like 10 calls a day. Do any of you get 10 calls a day from robots? Well, that's good. Oh, Malik does. Okay, I am telling you, this has to stop, right? It's really an invasion of privacy, almost. It's how it feels. But at any rate, by Clairaut's theorem, remember what this is, right? What this is here. Yeah, I agree, Hyunu. I agree. Right? So these mixed partials are defined as you see below there, and by Clairaut's theorem, they are equal to each other. How many remember Clairaut's theorem, that the second mixed partial derivatives are equal to each other? Okay, Charles recalls that. And it's been a little while. That was in chapter 11. But absolutely. So these partial derivatives, the mixed partials, you have like you have pluses, some are positive, some are negative, but the positive and negative mixed partials will, by Clairaut's theorem, they will cancel each other out, and you get 0. Hence, the divergence of the curl is equal to 0. Okay. Okay, so like in example 5 here, they want you to show in example 5 that the vector field, can't be written as and that's the vector field that we saw in example, it was example 4, I believe, right? We saw that vector field, yeah. Show that that vector field can't be written as the curl of another vector field. That is, the curl of some other vector field G cannot be equal to the vector field F. Well, what they do, you know, we showed that the divergence of that vector field was equal to Z plus X times Z, and so the divergence of the vector field is non-zero. Well, if the, let me go down a little bit here. Hold on. One moment, class. If the divergence of the vector field were, you know, when it's not equal to 0, okay, suppose, so we know the divergence of our vector field is Z plus X times Z. That's not equal to 0, right? But if it were true that our vector field F could be written as the curl of some vector field G, then the divergence of the vector field F would be equal to the divergence of the curl of G, and that would equal 0. But we know that the divergence of our vector field F is not 0. So we arrive at a contradiction. And therefore, this is a contradiction we arrived at. And therefore, the divergence of the vector field is not equal to 0. And so the vector field F cannot be in the curl of another vector field. Okay, are there any questions on that? Okay, well, let's continue on here. Let's continue on. So how can we interpret divergence in terms of like physics and engineering? Well, they have here highlighted again the reason for the name divergence can be understood in the context of fluid flow. My father was an expert in this. If you have a vector field that's the velocity of a fluid or gas, then the divergence of the vector field represents the net rate of change with respect to the mass of the fluid flowing from the point per unit volume. You are adding up partial derivatives, right? And those are rates. So the net rate of change is the sum of all those first partial derivatives. So divergence of F measures the divergence of the vector field measures the tendency of the fluid to diverge from a point. And if the divergence of F is equal to 0, then the vector field F is said to be what's called incompressible. Incompressible. Okay. Okay, are there any questions on that? Okay, I'll show you just a few more things here, and then I want to do a little example with you. But so, in terms of like notation, the divergence of the gradient is equal to the del operator dotted with the gradient. But that could be just thought of as the sum of the 3 second partial derivatives. So one moment here. One moment, class. One moment. One moment. Okay, so how many have seen the Laplace's equation, maybe in a physics class? I'm not sure in the literature, it says that Laplace's equation, which is a second order partial differential equation, is widely used in physics because its solutions occur in problems of electrical, magnetic, and gravitational potentials or steady state temperatures of hydrodynamics. And hold on, somebody chatted here that they have. Okay, Charles has seen that. Okay, so, Laplace's equation can be represented in this brief notation. Del operator squared F equals 0. Okay, so that is quite nice, quite nice. And actually, if we go to the next page here, I'll just show you something else because I want to try to make sure, I know that you might see this. Green's theorem, which you just learned from section 13.4, can be written in terms of vector notation. So again, Green's theorem is when you are computing the work that a force field does on a two-dimensional force field in a two-dimensional space, the XY plane. What does the force field do? What work does the force field do in moving a particle once around a closed path in counterclockwise, right? That's positive orientation. Well, if we the curl of a vector field, okay, if you regard the vector field on R cubed, okay, so again, Green's theorem is when you have a two-dimensional vector field, and then that means that in terms of a three-dimensional vector field, the third component would equal zero. Okay, computing the curl of F would give you just what you see there. The partial derivative of Q with respect to X minus the partial derivative of P with respect to Y, that times the K vector. And so the curl of the vector field F for a two-dimensional vector field dotted with the K vector would just equal the partial derivative of Q with respect to X minus the partial derivative of P with respect to Y. Absolutely beautiful. And so Green's theorem can be expressed using a vector form. Okay, I'm not sure if any of you have seen this in a class yet. That kind of notation. Again, on that integral on the left, that line integral, that circle just means positive orientation. So I just wanted you to be aware of it, in case you see that. And then there are other forms also of Green's theorem. But that being said, let me get to the example. Are there any questions at all? Okay, well, let me bring up this nice example here. Okay. So I'm going to give you a moment to copy this example down, and you should copy down the field too. I would say copy the picture. We're going to talk about divergence and curl in terms of like an actual picture of a field here. Okay, so let me give you a moment to copy this example down. Okay, all right. So what we want to do, and again, you can zoom on the right. You can use your zoom button if you want to blow up the picture a little bit. Here we are being given a vector field. Okay, we have a, hold on. One moment, class. Right, we have a picture of this vector field. And the first question says, is the divergence of the vector field positive, negative, or zero? Positive, negative, or zero? So, well, so let's remember how divergence is defined. Divergence of a vector field F is equal to the partial derivative of P with respect to X plus the partial derivative of Q with respect to Y plus the partial derivative of R with respect to Z. And, you know, our vector field F below here is equal to P times I plus Q times J. Okay, that's our vector field. So what is R equal to, class? That's right, Ellie, 0. Okay, because well, I could put plus 0 times k here, right? It's a two-dimensional vector field. So the vector field F would be given as you see here. Now, all right, so we need to think about then what's the rate of change of the P component of the vector field with respect to X, and then what's the rate of change of the Q component of the vector field with respect to Y. So let me go on the next page so we can talk about that. Well, all right. I'll tell you what. Maybe let's just take let's take here. Let's take here like this piece of the vector field. Okay, so I'm studying that portion of the vector field as X increases, right? I'm studying that portion of the vector field as X increases. And incidentally, I can go up here and I can study this portion of the vector field as X increases. So I'm going to just go across, right? When I look at the vector field to determine this first partial derivative, P with partial of P with respect to X, I'm going to focus on how the vector field behaves, just focusing on moving across the vector field in the positive X direction. How do the vectors, how do the first components, okay, of the vectors, okay, every vector has an I and J component. How does the I component behave as we move to the right? along um, along the vector field, strictly to the right. Are the vectors getting smaller? Are they getting larger? Are they not changing at all? What's your opinion? Looking at these two levels here. Juliana thinks with respect to the x direction, the vectors are getting longer, right? Who's in agreement with Juliana on that? Who agrees with her? Okay, all of you, very good, very good. Well, what would that tell you then about the partial derivative of p? What would that tell you about the partial derivative of p with respect to x? Would that be positive or negative? It would be positive. That's right. Because the p component, that's right, Ellie, that's right, Juliana, the p component increases with x. The p component increases with x. Okay, so if I go to the next page here, so what I did was I just took like one of the levels, just as a nice little example, one of the levels of the field. Based on the picture of the vector field, the p component increases with x. I mean, for these vectors here, these four vectors, let me ask you, what's the value of the q component for those four vectors, just in that example? 0, right? And it doesn't change. All those vectors are horizontal. And incidentally, if I go back to the picture here, and I'll go back there, and I were to look at like these levels here, this level here of vectors, does the q component change? The up and down portion of the vector, the vertical component of the vector, does that change? No. Does the vertical component of that, that's right, Ellie, does the vertical component of the vectors change here on the top level of vectors as x increases? No. That's right, Ian, that's right, Malik. So we can say then that based on the picture of the vector field, p increases with x, but also based on the picture of the vector field, q does not change with x. And so the partial derivative of p with respect to x is greater than 0, but the partial derivative of q with respect to x equals 0. And incidentally, the partial derivative of r with respect to x is just equal to 0, right? So what I'm doing is I'm trying to, I mean, you know, the curl, the definition of the curl is dependent on these partial derivatives as well. So I'm going to try to, you know, and there's 6 different ones, right? So I'm going to try to kind of knock them out, take care of them as we go. So copy down to here, and then I want to go back to the picture again. Please let me know if you have any questions. Okay. Now let's go ahead and look. Let's go back to the picture and let's focus. Let me write down the, again for our problem, the divergence of f is equal to the partial derivative of p with respect to x plus the partial derivative of q with respect to y. And our vector field f is equal to pi plus qj. So if I focus now on the y direction, partition the vector field so that you look at a level of vectors in the y direction. Well, what's happening to the q components of the vectors as you go up? The vectors seem to be tilting upward, right? As you go higher and higher in the y direction, the vectors seem to be tilting upward. Is that going to cause the q component of the vector to increase, decrease, or just stay constant? Good, Giuliani. Increase. Good, Ian. Increase. That's right. That's right. And everywhere you look in the field, if you just focus on a portion of vectors and look at how the vectors behave when you move vertically up the field in the y direction, in the positive y direction, the vectors are getting their, even though the q components of the vectors, the vertical components of the vectors are increasing. So this is going to be greater than 0, right? But what about now the partial derivative of p with respect to x? Well, hold on. Wait, hold on. We already took care of that, right? We took care of that, right? So I think I have, yeah. Let me just ask you this. Let me just ask you this. Okay, looking at this here, the partial derivative of q with respect to y is greater than 0. What would the partial derivative of q? No, hold on. What would the partial derivative of p with respect to y be? What do you think that would be? That's right, Ellie. It would equal 0. Because as you look in the vertical direction here, as you look upward, the horizontal component of the vectors stays constant. The length in regards to horizontal length is the same for the vectors, but the vertical length changes. And so we then get down to this part. Partial derivative of p with respect to y equals 0. Partial derivative of q with respect to y is greater than 0. And then here's the partial derivative of r with respect to y. That would just be 0. Are there any questions so far? Who's comfortable with what I'm explaining here so far? Okay, very good. Very good, Ian. Very good, Malik. Very good, Ellie. Okay, very good, Gordon. Okay, so now P and Q also don't vary in the z direction, right? Because again, your vector field F is equal to Pi plus Qj. So P and Q, those are in the XY plane. Those don't, they're not in going, they're you know, like they're not, there's no third component. So their partial derivatives would also equal 0. So now basically we have enough information to be able to answer the questions in this problem. Part A, the question was, is the divergence of the vector field positive, negative, or 0? And part B, it asks, is the curl of the vector field equal to 0? So I'll show you that on the next page. On the next page here. But are there any questions at all? All right, give me a thumbs up when you're ready to move to the next page, and we'll finish this problem. Okay, Ellie's good. Madeline and Juliana are good. Charles is good. Gordon's good. Ian's good. Okay. All right. Well, then here we go to the next page. So for part A, divergence is going to be positive. The divergence of the vector field is positive. And incidentally, let me just go to the picture. This makes sense because if we look at how the vector field's behaving, okay, either whether you move in the x direction or in the y direction, okay, or you know, a combination of both, what seems to be happening to the rate of change flowing from the origin or flowing from any point in the field? Do the vectors, if you pick a point, like if you pick a point, maybe I'll put it in red. If you pick some point in the field, and in this case the point would be xy, what do the vectors do as you move away from that point, you know, going in the positive x, positive y direction? What does the rate appear to be? In other words, if this were a fluid, like a river or a stream, and you're flowing like out this way, does the fluid or the river seem to be running faster or slower? The current. Does the current seem to be increasing or decreasing as you move outward from the point? Faster. Good. That means the divergence is positive. Good. Let me go back to the next page. Let me give you a moment to copy this down. I will be right back, class. One moment. Okay, please forgive me for that delay, everybody. So now let's look at here the curl of the vector field. The curl of the vector field equals the zero vector, okay? And are there any questions on that? All right, let me ask you this. So, well, yeah, okay. There were 6 partial derivatives that we had to compute in order to get the curl of the vector field, and they're all equal to 0. How many partial derivatives are there total, class? If you have like components P, Q, and R, how many partial derivatives are possible with three components. I was thinking of a different number. I was thinking of 9. Yes, because you can have that. That's right, Ellie. Thank you everybody for making, trying. Partial of p with respect to x, with respect to y and z. Partial of q with respect to x, y, and z, and partial of r with respect to x, y, and z. But for the curl, we only needed to compute these 6 partial derivatives. They were all equal to 0. And this means, if we look at our picture here, our vector field here, we're saying that the curl, let me just write it the way I want to write it here. Hold on. Okay, we're saying that the curl of the vector field is equal to 0. Okay, so this implies that our vector field of f, our vector field there, is irrotational. Irrotational. Right? When the curl of the vector field is equal to the 0 vector, the vector field f is irrotational. So if we were to put, like, at some point, any point, right? But let's just pick a point there. All right. Let's say this is like a river, and there's the current flow. Okay. And or like a velocity field. Okay, for current. Would, if we put like an object in the river, okay, in this river right there, maybe a little boat. How many have seen those little plastic boats that children play with, like in the tub? Those little plastic boats, or I'm trying to think of a toy that the children play with in the tub. I don't know. Does anybody have a rubber duckies? I don't know. A rubber duck. Okay, Juliana. Who can show me what if the rubber duck? Thank you, Juliana. All right, the kids love those. I don't know why, but so here's the object. There's the rubber duck right there. Okay. Can anybody on the picture here show me what path the rubber duck's going to follow? Can they take the pen and show me the path? Maybe in blue. Here, I'll set it for maybe blue here. Can you show me, starting at the point xy, the path that the rubber duck's gonna go in, based on that vector field of the current? Okay, something like that, right? Now, did the rubber duck? Thank you, volunteer, whoever did that. Was that Ian who did that, or Ellie, who was? I guess I. Okay, Ian. Okay. Thank you. So did the rubber duck rotate? Did it spin around at all when it went along that path? So in other words, Ian's right. Ian's right. He has a, well, now hold on. Here's a rubber ducky. Well, hold on. Let me put the rubber ducky down here. Okay. Let me put the rubber ducky right here. Okay. You remember from Calculus 2, how many remember direction fields in Calculus 2? Direction fields for differential equations. I mean, this is like a direction field, right? Gordon remembers, Juliana remembers. So the path that the rubber ducky is going to make is going to do something like this, right? I mean, is there any like spinning around on that? Is there any rotation? I mean, is there any swirling going on there? Well, Ian, let's see. Ian asks, hold on here. Ian says, won't the further right part of the duct be moving faster than the left part, making it spin counterclockwise? Well, it's going to turn. It's going to turn, but it's not. I mean, the curl of the vector field is equal to the zero vector. So the rubber duct, so that means this fluid is irrotational. Now, irrotational means that that the fluid is free from rotations. You don't have like little whirlpools or eddies in the water. The duct is turning with, but it's going with the flow. It's going with the flow. It's not like it's going with the current and getting spun around. You see what I mean? It's just kind of following the current. If you think about it, that rubber duct's going to follow the current, but it's going to follow the current, but it's not going to be. And I want to be a little bit careful here. Maybe in the picture, maybe I'm actually. Let me just see one thing here. Hold on, class. This is a good discussion. Good discussion. Yeah, I mean that's. Let me put that rubber ducky back here. At that red point. And it's flowing along the field, maybe like that. So the rubber ducky is turning as the current turns, but it's I want to say it the right way. It's not like getting like spun around, not rotating. That's how I picture it, Charles. That's how I picture it. The turning is not equal to the rotating. Okay, this is an irrotate. The vector field F is irrotational. So what I'm trying to sort of get you accustomed to is to, you could see this kind of problem. You'll see it in homework. Maybe you'll see a problem like this on your final exam. It's helpful if you just kind of be able to get a feel for what it means, for a rotational vector field and an irrotational vector field. Let me show you something here. I'll tell you what, I got something here. What you need is an analogy, right? Let me bring up something here. I got to go here. Okay, hold on. Let's see, Charles says, think of it as turning as moving with the flow field, rotating as independent of the field. Hold that thought, Charles. Let me show you an example here of another field. Now I can't write on this with my pen, but look at number 11 there. Can everybody see the field at the bottom there, number 11? Maybe give me a thumbs up. Okay, thank you, Gordon. Thank you, Charles. So if you were to put a rubber duck, let's say that's current. Let's say that's current in a river. So the bottom, like in the bottom there, the current, what direction's the current flowing in the bottom portion of the field in problem number 11? The current is flowing to the left, all right, to the left. Good. That's right, Ellie. Now, what about the top part of the field in number 11? Is the current flowing right or left? Okay, it's going in the positive x direction, right. Now, if you were to place an object right in the center of that field, if you were to place a rubber duck right in the center of that field in number 11, okay, what would the rubber duck do? What would the rubber duck do? It would spin. That's right, Ian. It would spin. So that is an example of a rotational. There's a rotation in the field at number 11. There's rotational. There's rotational. A rotational effect. That field gives it a rotational effect. Now, let's think a little bit further. What direct? So the curl of the vector field in number 11 is not equal to the zero vector. It's a non-zero vector because the rubber duck, when we put it there in the field in the center, in that way that current is acting, it's going to rotate. Charles, does that kind of help you feel the difference? Does that help you understand the difference between the rotational and irrotational? Excellent, excellent. Now another question for you. The curl vector is going to point in a certain direction. So is the swirling in number 11, is that swirling, is it going in the clockwise direction or the counterclockwise direction? The rotation. It's rotating clockwise. That's right. Okay, does everybody see that? That's right, Ian. That's right, Charles. But please let me know if you're uncomfortable. What I'm saying is if you put like a rubber duck in the center of that field in number 11, in the center, if you put a rubber duck in the center of that field, hold on here. Let me just, there, I'll make it. There's number 11. So we all agree that the curl of the vector field is non-zero, right? Because if we put a rubber duck right in the center of the field, the duck's going to spin around, right? Give me a thumbs up if you're okay with that. Give me a thumbs up. Let me make sure you're all good. Okay, good, excellent. Now, do we agree that the rubber duck would rotate in a clockwise direction? And by clockwise, of course, let me just hold on. By clockwise, I mean in this direction. This is clockwise, right? This is clockwise. Hold on here. Okay, Charles agrees. Okay, Malik agrees. Okay, so it's going in this direction, in the direction of the hands of a clock. I hope you can all tell time with a regular clock. I hope we're, you know, hope they still teach that. Okay, so fine. Well, all right. So the rubber duck rotates clockwise. Now, what direction is the curl? Is the curl below the XY plane or above the XY plane? Because in the book it says that the particles in the fluid rotate about the axis that points in the direction of the curl. So the curl vector has to be coming like directly out of the page, right? So it's either going to point upward from the XY plane or downward from the XY plane. What I want to know is, do you think the curl, if you think about the right hand rule, okay, what direction, if you curl your fingers in the direction, the clockwise direction in which the flow is occurring, okay, the whirlpool in the water there, that's right, Charles, your thumb points downward in the negative K vector direction, okay, negative Z direction. All right, are there any questions on that? So in other words, the curl vector would be, and I mean, it's going to be, I want to say this the right word, the curl vector is going to point in the negative Z direction. Because if you curl your hand think of putting your hand on that current there. Your fingers, if you curl them the way the current's going in the clockwise direction, your thumb is going to point downward in the negative z direction. All right, are there any questions on that? Who's comfortable with that? Maybe go ahead and give me a thumbs up. Okay, Ian's good, Gordon's good, Ellie's good. Excellent, excellent. Juliana, Malik, excellent. All right, well, very good. Well, what I'd like to do, let me stop the recording then.